So in this video, we're going to discuss the critical path algorithm. Along the way, we will define a few key phrases and we'll illustrate them as we need them. So we see that our first vocabulary phrase here is the critical path for vertex X. And it says for a given vertex X of a project digraph, its critical path is the path from vertex X to the end with the longest processing time, or the longest total processing time. Well, what does that mean exactly? Well, we can go from X to end. We see we have a few different choices on how we can do that. And we want to find which of those has the longest processing time. So why are we interested in the longest processing time? Well, we're talking about scheduling tasks for a project. And the series of tasks that have the longest processing time is going to be what backs up our project. And that's why we're looking for the longest of the processing times and their totals. So down here, I asked the question, how many different paths are there from X to end? So the first path is X to A to B to end. The second path is X to Z to B to end. And the third path we found was X to Z to Y to end. So now we want to find what is the longest processing time to get from X to end. So if we look at our first path that we wrote here, X is 7, A is 2, B is 4. That gives me a total of 13. The second path, X is 7, Z is 5, B is 4, and get a total of 16. And the third one, X is 7, Z is 5, Y is 3, and the total is 15. This shows us that the second path that we outlined is the path with the longest processing time to get from X to the end vertex. This brings us to our next vocabulary, which is critical time. Critical time is the sum of processing times for all the tasks in the critical path of a vertex. We've just identified this second path as the critical path of the vertex. That means that 16 is the critical time for vertex X. And you're going to find that we write critical times in square brackets and processing times in parentheses. So, the next question, which path has the longest total processing time? We identified that, XZBN, and the processing time is 16, and that's the definition of critical time for X. And can we identify the critical path and the critical time for vertex Z? So again, we'd want to write out the list. What are all of the different ways we can get from Z to the end? And we see we only have two paths this time, Z to B to end and Z to Y to end. So if we write these out, ZB end, the processing time from Z to B to end is 9, and then Z to Y to end, that has a processing time of 8. That means that the critical path and critical time for vertex Z is here. So ZB end is the critical path, and 9 is the critical time. So we'll put that in a bracket, a square bracket, next to vertex Z. So now we have something called the backflow algorithm, and it's a technique for finding the critical times for all of the vertices in a digraph. And it's easier than what we just did before. This way, we had to list out all of the possible ways that we can get between a given vertex and the end vertex. And the algorithm here, the backflow algorithm, is going to save us from that work. The backflow algorithm simply says work backwards, adding up processing times to get critical times, and take the largest critical times between any two vertices and add that to subsequent vertices as you work backwards. So let's see how this works. End is not a task, so its processing time is 0. But as I go backwards from end, I would add 0 to 4 and say the critical time for vertex B is 4. I would go backwards from end to y, add 3 to 0, and say the critical time for y is 3. But now notice that vertex Z can be fed backwards from either B or Y. And our goal is to take the larger critical time. The larger critical time is 4. We want to take the 4 from B and add it to vertex Z. That'll give us a critical time of 9. And there's only one vertex that feeds back into A, and that's B. So B has a critical time of 4. We add that to 2 to get 6. And now we say, look, X has 2 different vertices that feed back into it. Which one has the larger critical time? Well, we see Z does. So we should take the 9 and add it to the 7 to get 16. And now we only have one vertex feeding back into C. And C has a critical time of 10. So we work backwards from end. Whenever there's more than one vertex that goes backwards into another vertex, we take the ones with the larger critical times and feed it back. We take the larger because the one that has the most processing time is going to cause our delays. So we're always interested in adding the largest numbers as we work backwards. This brings us to our next phrase, the critical path list. The critical path list is a priority list made by arranging the tasks in decreasing order of critical times. Any tasks with equal critical times are sorted alphabetically. So we're going to look at our critical times, and we say which vertex has the largest critical time. We see that's X, so we'll list that one first. After a critical time of 16, the next in line is C with 10. The next largest critical time is Z. Then we have A. Then we have B. And finally Y. So the critical path list is simply a list in decreasing orders of critical times. If any of these two had equal critical times, we would just put them alphabetically in their spot of the list. That brings us to the critical path algorithm. The critical path algorithm says that we will now schedule these tasks using the critical path list as the priority list. And you see that now I have all of the tasks here with their task times. And this is an important point. Sometimes students mix up task times with critical times. You can only schedule according to the time that it takes to complete a task, not its critical time. The critical time is only used to help us identify what's going to create delays in our projects. So the first task in our list is X, and we say, can we schedule X right away into our timeline? And we look and we say, well, yes, X is connected to the start vertex. That means nothing has to be completed beforehand. We can put X in here right away. It's going to take 7 units of time. So I'm going to outline 7 boxes and say this is task X. Next on my list is C, and we say, can I schedule C right away at time 0? And we say yes, because C is connected to the start vertex. So we schedule C, and that's off our list. Next on my list is Z. Z only needs for X to be completed to be able to schedule it. And we say at this time in the timeline, X is completed. So we can schedule Z. That takes 9 units of time. I've outlined 9 boxes. And that is task Z. Task A requires that task X be completed, we see. So I can put task X over here. Task A over here, because at this point we see that task X was completed where A is being started. Next in the list is B. B can start as soon as A finishes and Z finishes. Well, A is finished at this point in the timeline, but Z doesn't finish until way down here. I cannot schedule task B right now. So then I look at task Y. Y requires Z to be finished, so also I cannot start Y until this point in the timeline. That means I have no other tasks to look at. I have no choice but to make this second worker idle for this time. And we see that at time 16, once task Z is finished, I can start both task B and task Y, because task B needed A and Z to be completed. A was completed all the way back here. And task Y needed C and Z to be completed. C was completed back here. So once Z is completed, both of these tasks can be scheduled. So B is 4 units. And Y is 3 units. And that means that once processor 2 finishes task Y, it is idle again for another unit of time. So from our graph, we want to identify the amount of idle time. We see 1, 2, 3, 4, 5, 6, 7, 8 units of time. I'm writing it as units because we don't know if this project is measured in hours, days, weeks, months, years, or so on. So we're just saying 8 units of time. The finish time is when the entire project comes to an end, and we see that that happens at 20 units of time. And those are the 2 points that we're looking for in the project. How much idle time was there, and how much finish time to get the project done.